Hi there. Good morning, everyone. I hope you had a great time yesterday and still recovering. Welcome to the fourth day of the summer school. So today we have Sweta Agrawal. She's a research scientist at Google, and she's working on machine translation and multilingual research. And she was a postdoc here at IST working in the sardine lab.
Yep.
And before she graduated from Maryland, where she worked with Marine Carpoit. So it's a pleasure to have her back and hope you enjoy your lecture. Yeah. The floor is yours. Welcome.
Good morning, everyone. Happy to be here. And today we will be diving into one of the most exciting advancement in artificial intelligence, transformers. You might not know the architecture or the name, but you have almost certainly interacted with the technology in the form of chatbots that we see everywhere. So chatbots like Gemini, ChatGPT, to search engines, to translation tools. And my goal today is to demystify what transformers are, explaining what they are, why they are a big deal, and how they are shaping the future of AI. Before starting, a little bit about myself. So my research focuses on building language technology that help reduce communication barriers. I work as a research scientist at Google Translate, where I work on creating and improving translation technologies that power Google Translate, and also understanding and improving the translation and multilingual capabilities of Gemini. And as we will dive into transformers today, it's impossible for me to overstate the importance that machine translation as a task has played, because we'll see that transformers was created. One of the primary problems that transformers tried to solve was machine translation, and it continues to be a challenging benchmark. And if you're interested in research on machine translation, please feel free to find me after the talk, and we can talk more about it. So before we start, let's do a quick poll. How familiar are you with transformers? Have you used it? Okay, I see a couple of hands. Do you know what is the key building block of transformers? Anyone wants to shout the answer? Yes. So we are going to talk more about what this attention mechanism is and how it helps power translation. Have you used transformers in your projects in some ways? Okay. And then have you implemented it yourself? Okay, I see a couple of hands. That's very nice. All right, so over the next two sessions, even if you are not familiar, even if you have not implemented it, we are going to go through all the nitty-gritty details of transformers. So at the end of the lecture, I hope you're ready to implement it yourself. That would be the good goal. So over the next two sessions, we'll start by dissecting first the core building block, which is the attention mechanism. And in the second session, we'll start where transformers made their biggest splash, text-based pre-trained models. But transformers are not just for words. They have been used for any modalities, including images, audios. So we are going to learn about how the core architecture of transformers was adapted to handle more than text. And by the end of the two sessions, I hope you have a stronger foundation on what makes transformers work. So before the advent of transformers, we often had an architecture designed per task. So for example, in order to handle images, we would have convolutional neural networks. For doing language modeling, we will use long short-term memory networks. For translation tasks, we would use encoder decoders, and similarly for speech, we would have its own module. The current reality, however, is that transformers have emerged as a surprisingly universal primitive for handling all these tasks at once, which is what we call these days as the foundational models. So as we heard, the core building block of transformers is attention. So let's talk about what this attention component is. The idea of attention was first introduced for neural machine translation task in the seminal paper by Barnadao et al. In 2015. And so let's see what they were trying to do. So here we have an input sequence in Turkish. So So we have this input, which is a Turkish sequence, and what we want to do is translate it into English. So the encoder would process this sequence of tokens to convert a fixed representation, and then the decoder's job is to create the translation one token at a time, right? So this is something that you might have learned in yesterday's lecture as well for sequence-to-sequence models. But imagine what the problem would be. Forcing this encoder to summarize all the information in this fixed dimension vector would mean that as our sequence length increases, imagine you're trying to read a book and you're trying to summarize this book with one single sentence. So this is what would be happening. We would have a very long sequence and just this one vector trying to summarize what the information is. So while for shorter sequences, or like this worked very well, what this led to was the information bottleneck problem. So what the paper proposed instead was to use attention. So what this attention allowed to do was at every time step, the decoder was allowed not just to look at this fixed length vector, but to attend at the individual tokens from the encoder. It was allowed to attend to the hidden states in the encoder, and we'll see how that would work. So the decoder could selectively focus on parts of the input that it finds important rather than just using the fixed length vector. Any questions so far? Okay. So let's do this more step by step. Let's say we have 4 tokens in our input, and what we have is the forward hidden representation, the backward hidden representation for each of the tokens. Sorry, the image is a bit blurry, but I hope it's still okay. So we concatenate the forward and backward representation from the hidden state to form our hidden representation for each of the input tokens, right? Now what we do is we add a small feed-forward neural network that takes as input each hidden state, so all the 4 hidden state, and the previous decoder state. So we'll take this decoder state, and then we'll pass the decoder state and each of the hidden representation through the small feed-forward network to compute a score. And these are what we call the attention scores. And in order to convert these scores into a distribution, we apply the softmax. And finally, to get a representation of the input, what we are doing is a weighted sum over our hidden states based on these alpha ij values. Now note what this alpha ij is. It's just like how similar is my current decoder state to my input, and I'm going to weight each of my hidden representation according to that. So as we trained this model, what this allowed the encoder-decoder model to do was it learned to pay attention, and it learned implicit alignment between the source and the target vocabulary. So if we were to look into what these alpha ij values are for, let's say, one of the input sequence, we can see that area is if this is my source and this is my target sequence, zone would have a higher weighting to area. So what the transformer architecture did, which was introduced in this paper, Attention is All You Need, by Vaswani et al. In 2017, they took this idea of attention and made it into the central building block. And unlike RNN-based encoder-decoder that we saw in Banadaus et al., transformers completely disregarded the recurrence. So they don't use there is no sequential processing, the sequential RNN processing. So let's see one more time what this attention is doing. So you can think of attention as a dictionary lookup. The way our traditional dictionary works is, let's say I'm storing as keys, country names, and as values, the city that is the capital, okay? And if I want to find out for a given query, let's say I want to find out what's the capital of Italy, And I can look into my dictionary to get the answer row, right? But attention, what it does, it's a soft lookup. So each query can be mapped to multiple keys. And all of these are vectors. So they are no longer a single element as we do in our traditional dictionary. They are d-dimensional feature vectors. So in order to find out what this query should map to, we take the similarity of this query vector to each of our key vectors. So that should give us a score, which measures how similar the query is to the key. And to get the final value vector, so we took the query, we computed the similarity, and then in order to get the result, the final value, we do a weighted sum, similar to what we did as we saw in Banadao et al. So my final value output would be a weighted sum over my value vectors weighted by these scores. And the scores are how, if my query is very similar to, let's say, key 2, my output value would be very close to V2. And we are doing a soft lookup to make sure that we are able to backpropagate through the network. So we are allowing the model to look into different key vectors, because at the end of the day, we would want to train the module. We would want to backpropagate through all the weights that we will introduce in a while. Any questions so far? Okay. So in practice, what happens is we obtain these query, key, and value vectors by multiplying with what we call weight matrices to either some input X, and these inputs are derived from embedding vectors or output of some hidden layers. So let's say I have embedding representation for the word thinking, for the word machines. What I can do is get the keys and values by multiplying the weight matrix for the query vector with x1 to get my q1. And we can do the same for the key vectors and the value vectors. And we introduce these weight matrices to transform an input into query, key, and value. The catch is the queries can be from the same input, so it can be from X or from a completely different embeddings, and we'll see where and how this is introduced. So again, here we don't have just one query, so we are not trying to find out a specific, the thing that gives transformers power is matrix multiplication. And this was designed to fit the hardware that we have. So in practice, we have several queries. So we have an input that is a matrix. We multiply it with the weight vectors to get several query vectors. So this is a query matrix, a key matrix, and a value matrix. And this might be the form that you are most familiar with for attention, the self-attention. So we multiply the query with the transpose of the key. And we have introduced here a small normalization term, which is the square root of dk, where the d is the dimension of so D is the dimension of the individual query vectors within this matrix. And what this normalization term does here is it's to prevent very large magnitude that we might get after multiplying the query with the key. So what happens if we have very large values is the gradients can be extremely small, making learning difficult. And then what we do is, how should we apply softmax? Should it be row-wise or column-wise? Can anybody try to answer? So note that we want to identify the similarity of each of the query with each of the key, and we wanted to convert this into a distribution using softmax. So should this softmax be applied row-wise or column-wise? Correct. So we would apply it row-wise, because note that when we are multiplying this query with the first key, we are getting the similarity. The first element in what comes out of this multiplication in the n by n matrix would be how similar is my first query to my first key vector. Now, the second element would be how similar is my first query with the second key vector. So my each row represents the similarity of the query with all of the keys. And this is what I want to convert into a distribution. Does that make sense? So now, once we have the distribution over how similar the query is with the key, we multiply this with the value matrix to get our final output vector. And this is what forms our single-headed attention. Sounds good? Okay. So now another key thing to note here is what we have is not just a single head, but multiple heads in our transformer module. Now, the way multi-head attention works is we won't have just one set of weight matrices to get our query key and value vectors. We would have, if we have 8 heads, we would introduce 8 weight matrices for each our query key and value vectors. And what this would do is, so for each of the weight, let's say we have an input X, we multiply it with the weight matrices for the 0th head and resulting in query key and value matrices for the 0th head. And that should, and then we do the single attention that we saw in the previous slide to get Z0, which is our output. For each of the heads, we would repeat this process to get output vectors Z0 to Zk, where T is the number of heads. Okay. So why do we do this is, let's say we are trying to understand what's in a sentence. We might want to look into different kinds of relationship. So the query might want to focus within a key as to what the syntactic similarity is or what the semantic similarity is. And what this head allows the module to do is to learn those different patterns. So given now all of these Zs, which are our output for each of the attention heads, to get the final value, we just concatenate all of them together. And in order to keep our weight matrices manageable, so if we were to just had full attention head and full weight matrices, the number of, the dimension of the parameters in our model would increase drastically. So what we instead do in practice is, let's say for a single head attention, you would have D dimension. If we are introducing M heads, we would have the dimension of this weight matrix as D by M. So this allows to have so we can still get the power of attending over different components, but at the same time keep the total count of the parameters manageable. So now that we have seen what a multi-head attention module is, let's try to understand the transformer architecture. So the model that was proposed in the original paper was an encoder-decoder model. And as you might have seen in the lecture already, the job of the encoder is to produce a representation of the input that captures its meaning, right? And the job of the decoder is to generate token step by step by looking at the encoder output. So whatever representation comes out of my encoder, and then because it's generating one token at a time, it can also look at previously generated tokens. So before we go into each of the components of this architecture, I just wanted to mention this very nice resource that offers line-by-line implementation. And you might want to check this out after the lecture. So now let's try to unpack what's happening in our encoder. The first thing that happens is tokenization. So let's say we have a string that says the monkey ate the banana because it was hungry. The first thing that we would do is break this string down into smaller pieces called tokens. And the process by which we do it is generally we use subword tokenization. Now you can think of subwords as basic building blocks that can be combined to represent any token in the vocabulary. And the good things about using subwords instead of full tokens is that we can represent new words that the model might not have seen during training by breaking it down into smaller components. And the second good thing is we can also teach the model to learn relationship between how words are formed. So depending upon how your vocabulary turns out to be, you can capture the notion. If play is my one of the subword, and ing, the second subword, is to form the word playing, I can combine play and ing, or I can do a past form played. So that could be combined with play and et. And this can help the model learn the notion of play and how it combines with other subwords to form full words. Now, let's say we somehow got a set of building blocks and we fixed the size of the building blocks. So let's say we got 32,000 subwords in our vocabulary. Now, what we do is we convert each of these subwords that we received into indices. This is basically forming a lookup of what's the index in my subword vocabulary that I created. Just a side note, the way we compute create the subword vocabulary, there are many different ways. One way you can think about is, let's say I have a huge amount of English text. I can look into patterns and frequency of things that can be combined, and I can sort them based on frequency. So I can start with individual characters and then see what is the most frequent bigram, trigram, and so on to form the subword vocabulary. So now we have this indices, but now these indices, they don't really capture anything, right? Like they are just telling us which subword it is. We encode each of these indices into a d-dimensional vector using an embedding lookup table. So what this will give us is a representation for, so let's say we divided this string into 10 subwords. We would have a 10 by d matrix that captures all of, that gives us the embedding representation for each of the 10 subword tokens. Now, but we have a problem, right? We converted each subwords into embeddings, but we have a bag of embeddings. The model doesn't know because there is no recurrence, right? Like we don't have any recurrent module anymore. So the model doesn't no longer know if we just use the embeddings, what's the difference between the monkey ate the banana versus the banana ate the monkey. And we know that these two are very different things. So in order to capture this notion of order in the language, we introduce positional encoding. So what positional encoding does, it's a clever trick to inject information about where the words are in the sequence where we started from. So we can convert each of our tokens into some index representation. And what we do is take our embedding vectors and then shift the input by some representation of these indices. So what we are telling the model is you have the embedding representation, let's say for the word the, but add an extra component that tells it that this is the first word in my string. Okay, so now you can think of the simplest way as I could have, if my context length, if the amount of tokens that I'm allowing my model to see is 1024, one simplest way is I can have 1024, a second embedding lookup that just takes each of the position and converts them into d-dimensional vector. But the field has evolved, and there are several different ways that you can do it. It's like, because if we were to do it with absolute position, the problem is the model no longer can support anything that goes beyond this length that it was trained with. So just to give a few more examples of how we can represent this encoding information, there was this paper by Shaw et al. Which introduced relative positional encodings. Now, we have our input representations and we convert them into the query key and value by doing the matrix multiplication, right? And what we did with the positional encoding in the previous slide was to add it to the embedding vector. But what they propose here is instead to capture the relative distance when we get the key and value representation instead. So what they do is introduce this additional weights. So these are also learned during training, but if there are, let's say, for each of the key and the value vectors, I'm supporting a number of relative distances instead. So if I want to capture, what this would have is, let's say for x1 and x2, we would have the position distance is 1. So I'll take a1 for the key and a1 for the value. And between x1 and x4, so you can see how it's looking at the forward and the backward tokens, and it gives it a little bit more flexibility. I can capture even for the last value, I can capture the relative distance with my keys and values. Does this make sense? Like, so what is happening is, let's say I am at token 512. I can still look at whatever number of elements I'm allowing to see. So let's say I'm allowing to see 256 tokens before. At any index position, I can allow the model to see that many tokens relative to its current position before and after. So it gives it a little bit more flexibility. And a second way of encoding this information is what was introduced in Sweta et al., what is called rotatory positional encoding, the rope embeddings. And this is what we use in models like Llama. So what they do is, instead of, we rotate our key and value vectors by theta here. So, so M is its current position. So this allows the model to, so it's capturing relative position, but in a different style than what we saw in the previous slide. So more details on this, like you can refer to the original paper to learn more about it, but it's like, just think about it as like there are more than one ways of capturing the position information about where the token comes in the string, okay? So once we have the output once we have the output which combines the embedding representation plus the position representation, we are going to apply a multi-head attention to it. And this is something that we saw just a few slides ago. So we have, let's say, embedding representation for each of the subtokens. We would multiply with the weight matrices for the query keys and values, and then compute the weighted sum to get our output, which are then concatenated to form our final output Z. And Note that we have different weight matrices to represent our different heads. So they would focus on different components of our input. So just to show an example, what would happen here is, let's say I'm looking at layer 0. You can see how each of the token focuses, the attention weights that we compute here. So what this component is giving us is how much focus each query is paying to each key value. And note that for each token in our string, we converted the token mon into a query and then made it look at how similar this token is for all the different subwords. So what this is showing you is what those alpha ij values look like for each of these subtokens. So if I were to focus on just layer 0, you can see that it's hard to show. Let me see. So the CLS token, for example, that might be the easier to look at. So the CLS token for layer 0 is focusing on the first sentence, because the blue values are higher, they're more visible for these tokens. Yeah. So now that we have the output from our multi-head attention, note that this whole operation that we did, it's still linear. Now you're going to ask me that we did apply softmax, and softmax is a nonlinear operation, but we are not applying softmax to the weight matrices. We are applying softmax to get the distribution. At the end of the day, we are doing a weighted sum over our value vectors, which is a linear operation. So hence, we need to introduce this second component, which is a feed-forward network. And what we are doing here is we are taking the output of the multi-head attention. We are doing a projection to a much larger space, applying the ReLU nonlinearity, and then contracting the vector back to the D dimension. Okay, so what this expansion is telling the module to do is look at these individual, so we have all the individual vectors for all the tokens that we had in the previous step. The feed-forward network is telling process each of these tokens independently, look at what patterns exist within this embedding vector, and then try to extract the most relevant information. And there are papers that show that this is where the most of the work happens within the transformer module. So the first layer, the expansion layer, its job is to recognize specific patterns within the vector that came out of the multi-head attention. The ReLU activation is then made to fire on, now that you have identified the pattern, capture the most important pattern, and then the compression layer, the contraction layer says, given this pattern, give this output. So it's key and value in that sense. So once you have identified what the previous, so I have a d-dimensional vector, I'm trying to identify what this should map to. So in that sense, it's a key value lookup. And after this layer, what our representation now include is for each of these sub-tokens, we don't just know what the relationship of this token should be for all other words, but we also know that what this word should act as, what's the role after this feed-forward layer. Then we have the last component, which is an add and norm. So what this add does is it adds a residual connections, which helps gradient flow when you have very deep networks. So this was first introduced in this paper, Deep Residual Learning for Image Recognition, and they were trying to train a super deep network. What would happen is when we backpropagate, we are passing the information on how the module should be activated at each layers. And as the layer goes deeper, the information that is retained for each of the subcomponents, they start vanishing. So in order to make sure that the gradients can flow smoothly, what we are adding is So this was our feed-forward network. All we do is add back the input vector to form our final output vector. And what this allows the model to do is also learn identity operations. So let's say if my module is not useful, I can just simply take this shortcut path instead. The second part that we are adding is a layer normalization module. And this is to, we are basically standardizing all the elements in our vectors to a unit norm. Um, So what we want to have after the layer normalization is to have a mean of 0 and standard deviation of 1. And this is to make sure that as we pass through different layers in our network, we are making sure that the modules are operating in a given data scale. So the scale of the values don't change through our networks. Yeah, so given this process of passing through the multi-head attention feed-forward network, add and normalize, this is repeated n times. And what this gives us at the end of the day is a heavily processed version of our inputs. Now, let's see what happens in the decoder. So the goal of we are trying to generate each token at a time, predicting next token probability by looking at the previously generated tokens. So if we look at self-attention module, it allows the model to see all the tokens that came before and after. But think about what's happening during inference. We are only generating a single token at a time, and we don't have information about the future. So our training should follow this protocol, right? So in order to capture that, what we do instead is we pretend we have all the information that we need, and we compute the full attention matrix, but we would mask out everything that comes afterwards. And we mask out, which means that we are going to set the values in our attention matrix to negative infinity. And what this would do is it would hide all the tokens that come afterwards. And this would make our training follow the same thing as we would do during inference. And this is what we call mask multi-head self-attention. So now my decoder has looked at what it has generated so far. But remember, we also created this very good representation of what our input sequence was. And let's say we are trying to translate a given text into another. We would want to know what was in the input. If I am translating an English text into Hindi, I need to know what my English text was. So I do need to look at what my encoder gave. And this is where the difference comes in. So remember in our initial slides, we saw that the queries can be from the keys and the values in this attention module. They are computed using the encoder states, but the queries, because we are trying to see at the current time step, where should I pay my attention to? So my query comes from my decoder, but my keys and values, they come from my encoder. And this is what we call the cross-attention module. So in the cross-attention mechanism, we take the encoder output, we create the keys and the values vectors, we take our decoder output, we compute the query vectors, and then the query vectors are multiplied with the key to get our attentions, and we do a linear combination with the value vector to get the final output. Any questions?
Sorry, I didn't want to interrupt, but can you explain better how we get the vector representation from the token. I mean the vectors x1, x2, because at the beginning we create tokens from the words. So we had the numbers, I remember 712 and the second number.
Yes.
Okay, so we have these indices, and then it's not clear how do we get the, if I'm not mistaken, 512 dimensional vectors. Yeah, it's not. Can you explain better that?
So, okay. Do you mean in the encoder or here in
The encoder.
in the encoder? Okay. So let's see what's happening here, right? So I started with my input X, and that's 512 dimension, right? Now this 512 dimension vector input is converted into query key and value, right? And we multiply the query with the key, and let's say there is just
No,
one
no,
element.
not that part.
Yeah.
How do we get the vector? I mean, how can we get this vector? Because firstly, we have, I mean, the words,
Yes.
the sentence, and after we have the tokens.
Yes.
Okay, so we have the indices,
Yes.
and after we have these indices, we want to, I mean, switch on the neural network. So we need a vector. So the question is, how do we get these d-dimensional vector?
So that's our embedding lookup table. So that's like the first set of weights that we introduce here. So imagine you also add this 32,000 by D dimension matrix in the set of vectors that you're trying to, in the set of matrices that you're trying to learn during training. So this is just an additional weight matrix where you look up each of the token to get that d-dimensional vector. Does that make sense? So this
Okay,
is,
so there is
yes,
a
there
linear
is
transformation.
Yes.
And we
yeah.
learn this matching during training?
Yes.
Okay,
Yeah.
thank you so much.
Yeah.
So basically we do a reduction, not a reduction. I mean, yeah, somehow we imagine that you have a vector with all the indices. Then we create another vector, which is it's bigger because the dimension is 512.
Yeah.
Okay.
For each of the tokens.
Yeah.
Yes.
Yeah. Okay. Thank you.
Yeah. So we pass through this cross attention module.
Sorry,
and-
Sweta?
Yes.
There's a question?
Yeah.
Sorry, I I never quite understood how the queries are learned. If you could like go a bit more in depth on that. I know that that was before, but I never quite understood that process. Maybe you could explain it.
No, it's okay. So remember let's start with the embedding matrix, right? That is learned. Now we have a few set of more matrices. So imagine if we only want to do attention once, we have a weight matrix that is going to take, that is what we multiply with my input that came out of the embedding lookup table to get our query vectors. So the query itself is not learned, but the weight matrices that get multiplied to the input, they are learned. Does that make sense? So we have those additional weight matrices, right? So here, once we have the embedding representations for each of the token, these are what we are introducing and we are learning. So when we multiply this with the weight matrix, that's what gives us the query key and value vectors. When we train the module, which is what we'll see in just a few slides, when we backpropagate through the network, we update these weight matrices, and that's how the query key and value vectors also gets updated. But the query key value vectors, they are just like a product of whatever input is given multiplied by these weight matrices. Yeah. It is turned off, but it's. It's on or off? Yes.
A short question. Is the embedding block trainable during the training transformer?
Yes.
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 But I think maybe we have some problem here because we try to update some random variables in the transformer, but the embedding block is trained before. So maybe it can change the embeddings so a lot.
So we are always doing random initialization. So even the embedding lookup table, it's randomly initialized. And once we start looking at our input-output sequence, the one that we are trying to learn from, and I'll show what this learning mechanism is, we are moving every weight matrices that we introduce, which has random values in a specific dimension that would minimize the loss. And once we define the loss, even the embedding lookup table, it's not, we don't initialize them with anything previously learned. They are initialized as random matrices.
Thank you.
Okay, so what we are now doing is once we have passed through our multi-head attention layer that let it look at the decoder state, the encoder state, we added feed-forward network. What we get is d-dimensional feature vectors. Now, we want to predict what should come next, right? So we want to predict what token should be generated. So we add an additional linear layer that's taking this feature representation and projecting it to a V vector. So V is the size of the vocabulary. And what we get out of this linear layer is logits. And now we apply a softmax to get the distribution over our vocabulary. So this probability P is this distribution that comes out from our decoder module. And to train the model, what we use is cross-entropy loss. So at the end of the day, what we got out of the entire module was a V-dimensional vector. Let's say I was trying to generate this sequence in my decoder, which was I saw a cat. And this is what we are trying to generate now is cat. What we would do is convert this cat into a one-hot representation over my vocabulary. So this would have 1 at the position of cat and zeros everywhere else. And we have the probability distribution from our encoder-decoder module. Now, what the loss is doing is telling it is this should have the highest value. So make adjustments to my weight matrices so that I can increase this specific value and decrease everything else. So when we say we are training a model, what we are doing essentially is showing it millions of examples to learn where to move those weight matrices such that I'm predicting the correct token at each time step. This is how the learning works. And so now once we have those probability distribution at inference time, what I can do is if I'm trying to translate a new input string, I can generate one token at a time by just taking the token that has the maximum probability. This is what we call greedy decoding. But now that we have this architecture of the transformer, I'm going to make the statement that it's useless in practice. We cannot use it during inference. And the reason being, it's very inefficient. Note what's happening at each time step during our inference. We get, let's say we are trying to generate one token. We compute the query key and value vectors. We compute the similarity. We pass through the decoder to get the prediction. Now, when we generate the second token, we are repeating all of this process again. We are taking the past two tokens, converting them into key value and query matrices. We are computing the attention score and passing through the entire network to get the probability distribution. Now, there is a redundancy in this operation, right? We are converting the same previous tokens that we saw into key value vectors. And we can save compute by what we call as KV caching. So instead, let's say I'm trying to generate the fourth token. What I can do is instead of recomputing the key value vectors for all my previous tokens, I can store them somewhere in my memory. And I would only compute the similarity between the current query with the stored key values and the current key value. And this is one of the most important things that you need to do in order to use transformers in practice during inference. And the size of the KV cache, the amount of key value vectors that you are willing to store, is what makes the context for generation. Imagine you have only so much memory to store 512 key value vectors. That's what is going to define what my context size is. Without defining this KV cache, we would be repeating a lot of the operations that are considered that would be redundant. We don't want to recompute the key value vectors for all my previous token at the current generation step. And this is one of the crucial difference that is important to make them efficient in practice. So we saw one of the ways to generate a token using the decoder, right? Like we could use the token with the highest probability, but there are alternative things that you can do. Is there a question? Yeah. Sorry?
What was the quality increase for the model? Also generation.
What is, can you repeat just the last part?
Yes, if we don't use KV cache, if we generated the next token, and then we wanted to recompute previous key values based on the new generated token, will the quality of the model improve?
No, because it's the same values. You're not computing new values, right? What's happening is, let's say I'm looking at the third time step, okay? The keys and the value vectors for my previous two tokens would be exactly the same as we computed in the previous time step. They won't change.
But if we wanted to consider the generated token also
Yes.
to calculate the score with the next token.
Yeah, so that's the only computation that we are adding. So if you look at here, we are adding the current token. So we are taking the current token, computing the key value, and putting them in the cache for my next token. But this key value for the current token is still generated. We are just reducing the previous, we are just like caching the previous tokens. But we do need at the current time step to compute the current key value. So we are not skipping that step.
Okay.
Yeah.
Question?
I can see in the OpenAI platform, there is an option named cached input, and it's so much cheaper than the default one. What is the difference between cache input here and the cache that you mentioned there?
I think I would need to check that, but I can follow back after during the break in terms of what the difference is. I'm not sure like what caching there would mean, because there are several ways that you can cache it, like cache the information. To what extent you are caching, how much information you are caching, that could vary.
I'm not sure, but they just mentioned there that they have a caching system for decreasing the cost of their systems. Yeah.
I can check and
Thank you.
we can follow up on that. Yeah. Any more questions? Okay, so we saw one way of generating a set of tokens at inference time, right? But instead of taking the token with the maximum probability, we can do something more. So we can sample from the distribution. And why would we want to do that is to get more diverse responses. One of the reasons why we like, for example, if my, even for translation tasks, let's say my input is I want to translate, our previous example, I saw a cat on the mat into French. There could be many different ways of saying the same input in French. And by greedy decoding, we just get one of the output. And by sampling from the distribution, we would be able to get multiple different sequences in French that map to the same English input. And one of the ways we do sampling is also called ancestral sampling, is by doing temperature scaling. This lets us control how peaky we want the distribution to be. So if we set the temperature values to be very low, we are essentially doing greedy decoding. And when we set the temperature to be very high, we are really sampling from anything that comes in the distribution. So even if it's a token with very small probability, we would sample this token during generation process. So alternatively, what we can do is what we call top K, top P sampling. So what we do here is to truncate the distribution in top K to the top. So we take the probability distribution, we sort the tokens according to their probability values, and then we take just the top K tokens. And what this allows us to do is to prevent the tokens with very low probability, because we don't want to generate them during the inference process. The difference that arises is if I were to do top 4, and if I have a distribution like this, where there are multiple tokens that contribute with different probabilities, versus if I'm doing top 4 in a distribution where 2 of the tokens are more likely, I'm still getting those low probability tokens. So with top P, instead of what we do is we make this flexible. So instead of having a fixed number of tokens, we take the top tokens that contribute to a specific probability value. So let's say I'm going to take the tokens that have 80%, the top 80% probability. So what this would do is, in this scenario, if my cutoff value is 0.8, I would only consider the top the top 2 tokens in the current generation process, instead of taking the top 4, like in top K. Now, there are variations that mix and match between the two to get the best of both worlds. And there are other sampling techniques that you can use during generation. These are just a few of them. So now the final question, given that we have the architecture and we know how to generate tokens with this architecture, is why did transformers take over? There were just 2 key factors. It had unprecedented performance, and it had remarkable efficiency. So you would imagine that by having all those weight matrices, we have too many parameters to learn from. But remember that all these matrix computations, they are happening in parallel. Even at the decoder time step, with the causal mask attention, we are still doing all the operations in parallel and masking out what's unnecessary. So there is no sequential operation anymore. And when transformer was applied to the task of machine translation in the original paper, even with the big transformer module, which had many more parameters, it outperformed many diverse architectures that came before. And this was a very strong key result at the time. So in conclusion, it was just not any other incremental improvement. It was an architecture that showed capability not just in performance, but also in the number of flops required to train this model by just using parallel matrix computations. My voice keeps repeating. So let's quickly break down what is the computation, the total computation done within this transformer module. So when we do attention, we are doing an n square d. D is the dimension of the embedding vector, and we are looking, each token looks at every other token, where n is the sequence length. So we have this n square d computation. Now, this quadratic n square computation is what has led to an entire field of making this operation faster. So the goal is simply, can we get the power of full attention without paying the full quadratic price? So one thing that we can do is, in this sparse attention module, what we say is, instead of making each model focus on every other tokens, can we pay attention to only a subset of tokens? And in the low rank kernel matrices, what we do is, instead of computing the full product between the query and the key matrix, we decompose those matrices into smaller components, and then we do a matrix computation that is a bit cheaper. Another way we can think about improving efficiency is, remember that if we have 32 attention heads, we need 32 key vectors, 32 value vectors at each inference step to be stored. What this paper instead did with the multi-query attention is, what if we only need one perspective for the keys and the values? So they combine the keys representation into just this one D-dimensional vector. So while this makes, without losing much performance, you are only storing one key and value vector at each inference step, which gives you much more flexibility on how you want to use the memory. But this reduces quality. So in a follow-up paper, what people have also proposed is grouped query attention. So instead of having a query vector look at a key vector that is the average of all the keys, you can have keys shared between different query vectors. So this gives you a good trade-off between just having one key value vector versus the number of head equivalent key and value vectors. So as a summary, as we bring things together, there are two things that we would want to remember. The first thing is, what transformers did was to remove recurrence by representing the input in form of key value vectors. And so instead of having sequential processing between each of the tokens, we allow in the encoder each token to look at all other tokens. And at the decoder, we apply causal mask attention to let the model look at the encoder representation and the past tokens. And using matrix multiplication, we have very fast. Using matrix multiplication, we are using the hardware that is now designed to support those faster operations, and this gives training transformers a lot of efficiency. So I'll stop here for questions before we move to the second session. Yeah.
Hello. Yes. So I have a question on the multi-query attention and grouped query attention. I was wondering, could you introduce a bit what is the motivation behind these two structures?
So the main thing to remember here is, let's say you have 32 attention heads, right? So if you have 32 attention heads, and for your KV cache, you are computing for each of the attention heads, you are computing key, value, and query vectors, and you're storing them in your cache. So what if we could reduce that KV cache size? So what if we could only store sum of the key and value vectors? That's the main question that we are trying to answer. Because reducing as the sequence length grows, you can imagine that if you are at step 100, you have cached all the query key and value vectors that came before. And if you have many attention heads, you have a lot of information that you're storing in the cache. So with the multi-query attention, you still maintain different query perspective, but you are only storing one key and one value representation, which is the aggregate representation of all the 32 heads. So this can drastically reduce the memory size for you, right? Like instead of having 32 values, you only have one now. So that's the main motivation. How can we reduce the size of the KB cache? But because we are compressing all this information into just one vector, we are losing out, right? Like we are losing the different perspectives that different heads were bringing in. They are getting aggregated. So instead of that, the grouped query attention, it lets a set of keys. So instead of storing all the keys or just one key, we are trying to find a middle ground. Let's just store 4. So let's say we want to have 4 key value vectors stored instead of all the 32. So this can give us a trade-off between the amount of information that is retained versus the size of the memory that we are using to store that information. Does that answer it?
Yeah, thank you.
This grouped query or the aggregated one, did it lead to a drop in performance?
So at least according to the paper, I know for the multi-query attention, they did see a slight drop in quality, but it was not significant because you're doing a trade-off at the end of the day. So this did lead to a slight decrease, and I think which was the main reason to bring in the group query attention.
Okay, thank you.
Hello. I was wondering, these large language models are non-deterministic by nature. Where does this non-determinism come in?
So, so when we do the matrix multiplication operation, note that we are representing each value with a certain precision at the end of the day. So if I have, and as the model size grow, if I'm using a 32-bit precision versus 16-bit precision, depending upon which CUDA kernel I used, which hardware I used, the exact precision that is being at the end of the day stored to do the computation, that changes, which makes them non-deterministic. Does that help? Yeah.
Yes, yeah, thank you.
So I have a question. I see some architectures that sometimes have like self-attention, sometimes have like cross-attention. How do you choose the both of these methods? How do you choose like the best one? And yeah, that's my question.
Yeah, so it's not about like choosing the best one. It's like they are all doing a very specific thing. So for example, the multi-head self-attention, we have they have the query key and value vectors computed from the same input. So self-attention here means that I'm looking at my own information and I'm trying to gather information from my nearby tokens, right? When we have an encoder decoder module, we know that there is something called the input that's giving us an additional information that I'm trying to look at. So cross attention is basically when you want to have, when you are trying to merge information from two different things, right? So you have the encoder input that gives you your actual values of what's stored versus your current decoder that's telling you what you want to generate, which forms the query. So they have different use cases at the end of the day. So self-attention is I'm going to only look at what's around me, and I'm going to look at what's with me. versus cross attention is I'm trying to look information from a different input altogether. And we need both perspectives in an encoder-decoder module.
Hi, so I wanted to know how important is it to train the token embedding table? Like if you didn't train it and just sort of had randomly initialized embeddings and then went through your data. Yeah, like is learning a specific feature representation for each token super important, or could it still learn with randomly initialized embeddings?
So it can still learn from randomly initialized embedding, but you do need to update it as part of the training. Because what the training is telling you is change everything that comes before in the direction of what would help me make the correct prediction at the correct time step. So we do need to update the embedding matrices because that's where the input at the first stage comes from. But it's okay to have them randomly initialized because I'm going to make them move in the direction that I want during the training process itself.
Right, but what if you just kept it untrained and then like, do you think it would still learn or the rest of it?
Yeah, I would be surprised if we would have just so you are saying if I have a random embedding matrix frozen,
yeah,
and I'm updating everything else, can I still learn? I'm not sure if that would work.
Okay.
Yeah.
Thank you, Sweta, for your very interesting introduction to transformers. I was curious if you know of an approach for group queries, because they still do some average over several queries. And the thing is that you don't know where basically the cut between the groups are. So you might cut in the wrong part. So do you know of an overlapping grouping? I would expect that there are maybe second lines of groups. One is so basically just an overlapping, like with chunking and overlapping with a stride. That makes sense.
Yeah, so I think like when they are sharing the keys here, they are doing this again with like so what you're saying is, what if I want to share the same key but with different queries, right? Like here it's fixed.
Well, not necessarily. So for instance, as in your translation example, several that example relates to tokens, but it can be expanded. Several words inattention account for several other words, but maybe in reverse order. So if you cut for the groups in between the full the full term or the full phrase, you might lose information.
Yeah, so we are not doing that at the token level. This is at the heads level.
Yeah, I understand,
Yeah,
but
yeah.
I would expect that the same problem might arise here. So another rephrasing for that is, what if I keep the same number of groups, but I would randomly select which queries would belong to those groups?
Okay. Might need to think more about
Yeah,
it.
we'll discuss more. Thank you. Just a thought, because this might count, I would expect. Thanks.
Should I start? Okay. Okay. So let's start our second session. In our last session, we took a deep dive into the transformers architecture and its core module attention. In this session, will connect that knowledge into the biggest shift in AI, which is using transformers as the base for pre-trained language models. So before we dive into how these pre-trained models came into picture, I want to start with what did transformers enable. So let's talk about what has changed and emerged in the last couple of years. The first point is scalability. So we have started training models that are billions of parameters on terabytes and even more of text, which is much more than we were doing a couple of years ago. The second is generalizability. We no longer train one model per task. We don't have one-off brittle models, but we have what we call foundational models. So the same model that is capable of solving multiple tasks at the same time. And third, and one of the surprising ones is reasoning capabilities. So as we learn to scale the number of parameters in the model, we have seen that the current models, if you have interacted with Gemini or ChatGPT or other models, you know that they can reason. So if I'm trying to solve, let's say, a math problem, and if I ask the model to think step by step, or let me walk through the solution step by step, it gives me a set of steps that leads to the correct answer. The fourth one is handling long-range dependencies. So now you can upload a PDF or part of the book to these chat-based models and ask questions about localizing a specific information, which is something that we were not able to do before. And finally, multimodality, which is the core principles of the transformer, which is to attend to different part of the input. It can be applied to any modalities, including images, text, videos, as well as audio sequences. But every revolution, it has a starting point. So the first one came in with this paper, Improving Language Understanding by Generative Pre-training, by OpenAI in June 2018. And what they did was they used the transformer decoder module. It had 117 million parameters. And what they did was to train this model on a massive data set of web pages and books. And all this model was trained to do was predict the next token. So we took all this data set, feed it to the transformer, and asked it to make sure the next token is predicted correctly. So this training was done over billions of words, books, web pages, and at the end of the day, you had a model that has seen a lot of information of text. But what do we do with this model? So they took this pre-trained model. So that's our decoder-only model that was trained to predict the next token with all its rich language representation, and then applied what we call discriminative fine-tuning. So they took the transformer model, they take as input, let's say you want to do sentiment analysis, you pass your input, and on the output, you add a small layer that can do classification as, let's say, the sentence has positive or a negative sentiment. So by using just this pre-trained model, they were able to pass different classification task input, train specific heads that can do prediction over the classes that you want to generate. And the results were that you could, by doing this discriminative fine-tuning, GPT-1 was able to outperform existing results on 9 out of 12 tasks. And this was the first time that they showed that unsupervised pre-training works. So you can actually take a model, make it learn the next token prediction task, and fine-tune this model to do other things, like specific tasks like sentiment prediction, multiple choice answer classification. And what this did was a single model could be used to generalize to multiple different tasks. this is not something that we did before GPT-1. So the next step was to take what GPT provided as a blueprint, which was to pre-train a model, fine-tune for the task, and apply it to a different module. So just a few months later, Google researchers asked this question as to, so remember in decoder, you predict one token at a time. So you only see what has happened before. You don't see what comes next. So they were asking, what if the model could see information on both directions? Can it help build you a better, a more richer contextualized representation? So unlike GPT-1, what they did was to use an encoder module, and what they were trying to get out of it was to let the model see things in the past and the future and get a better representation out of it. But if we were to let the model see everything, the task would be too simplistic. So if the model can already see the whole sentence, what does it learn for the current word at the end of the day? So their solution was to introduce what we call masked language model objective. And it's very simple. So what you do is, let's say I have a sequence of tokens. What I do is mask a portion of the tokens. And now the task is take the encoder architecture and make it predict the tokens that we masked in the first step. So now, depending upon how much information you mask, the model, it's not a trivial task. It's not just trying to predict the current token based on all the information that's present around it. It's trying to build representation that lets us identify what should be the word that should fill here. So this simple objective, it gave BERT power to build contextualized representation, and how it was implemented in practice was they masked 15% of the input tokens following the 80-10-10 rule. So 80% of the time, we would replace the subword in my input sequence with mask and actually predict it. 10% of the time, I'll replace this token with a random different token, and 10% of the time, I'll keep the token as is. So this is what would happen here in step 0. And then the model is for each, remember that encoder gives you representations for each token that you fed. And what you do is for the tokens that you have masked, you are just making the model learn what should be filled in at that specific position. So what this allowed the model to learn is how a word is represented in a sequence. Before this, every token would have a static embedding, but now note that depending upon the sentence, if you are using the same word in different sentences, they would form different representation, because the context is what would determine what the current word's contextual embeddings should be. But a lot of how we understand text is not just about how a word presents itself in a context. We also learn about language by how sentences interact with each other. So following that, the next objective that BERT introduced was to add a different sentence prediction task. So in this objective, what they did was they would take a document or a sequence of string, let's say, that forms 512 tokens, randomly split this string into 2. And so because what this task is doing is predicting whether 2 sentences are related to each other. So in order to form data set for this, you can imagine taking the first half of the tokens and the second half of the tokens from a given document and predicting whether they are related to each other. So that would be a yes when they come from the same document, and it would be a no if my first segment comes from a different document than the second segment. And what this let the model learn is how sentences are related to each other. So sentences, by sentences I mean segments more. It's not exactly just one sentence. It's a sequence of sentences following a segment. So for those who follow this literature, they know that now we don't, in the future, after BERT, the next sentence prediction task was found to be unnecessary, and it actually improved performance by removing this on a different model that we'll see in just a bit. But at least at the time, this task also made sense because you wanted to learn how word form a sentence and how sentence and segments are related to each other. Yes.
Thank you very much. So I have one question. So during the training, did they train simultaneously the embedding vectors and the classification at the same time, or they did it like separately?
Do you mean whether all they were predicting was just the classification or the whole? They were doing the whole.
No, they did mask modeling prediction and same time while they training the classification, or they did like first mask prediction and then they did classification prediction training, or they did it at the same time?
I might be wrong at this, but I think they did it at the same time because both objectives were trained together. But
Okay.
I might need to you might need to double check me on this. But they were using both objectives during pre-training. So it was not a second step. It was like this was happening to get the pre-trained encoder.
Thank you very much.
Yeah. So after BERT, because we were masking those 15% of tokens randomly, a follow-up paper asked what should we mask in the first place? Like right now we were masking random tokens taken from the segment, but can we do better? So span BERT, instead of masking individual tokens, they masked a span of tokens and asked the model to predict the entire span instead. This was to enable the model to learn deeper relationship between the masked tokens as well, and they form their own. So if I'm only predicting one token versus I'm predicting multiple tokens, the difficulty of the task changes. And similarly, like we could take 15%, masking 15% as a thumb rule, but we can also investigate whether we always need to mask 15% of the token. So in another paper in 2023, there was a follow-up to investigate at different scale, do we always mask 15% as the role? And what they found was, at least for bigger models, you can actually optimize the model better by masking more tokens. So if I were to increase the size of BERT, masking 40% of the time is better than 15% of the time. So there were all these questions that were answered post we have the initial BERT paper.
Sorry. What is the main difference between encoder, decoder models and decoder only? I'm here.
Sorry, yes.
What is the main difference between encoder, decoder models like BERT and decoder only like GPT? Because sometimes we say that it has just decoder, but I think that both of them need some representation to predict the next token. So what is the main difference here?
So just to clarify a couple of things. So BERT is encoder only. It's not encoder decoder. And then GPT is decoder only. The main difference would be how you implement attention. So for example, in the encoder, if you remember, what we had was self-attention. So every token was allowed to attend to everything that came before and everything that came afterwards, right? With decoder, what we are doing is we have causal attention. So at every time step, the model is doing a generative task. It's not trying to form a representation of the input sequence. It's kind of doing that for the part of the text that it has generated, but the code thing is different. So for decoder, we are generating one token at a time, only looking at what has been generated so far. And we don't allow future, it doesn't get to see future tokens. It's trying to generate rather than understand what's in the input.
So the future tokens are masked, the attention of future token, yeah?
Yes, in the decoder, we mask the future tokens. We are trying to generate tokens, whereas in encoder, we are trying to form a representation of whatever was the input, and we are trying to understand the input. So the thing that is being done is the role that encoder and decoder plays are different in that way.
And how about encoder decoder model?
So with encoder decoder model, there is an input and an output, right? So you're trying to understand the input and then form a transformation in the output. We'll see how they unify over different models. So we'll talk about a few different architectures. So we saw how GPT was decoder only, and now we have BERT, which is encoder only. But we'll form this as to, we are trying to unify all of this over different modules.
Yeah, thank you.
So now that we have the BERT model trained over billions of text, and all we are doing is, remember that with the BERT model, we take all the text that we have and we form these examples for the sentence prediction task by masking, by training whether they are related or not, and for the words, predicting which words were masked. And let's say we did this over billions of text. What we have at the end of the day is a learned encoder. But what do we do of this pre-trained encoder? We fine-tune them for the specific tasks that we want to do. So an example would be, let's say I want to predict, again, similar to what we did with GPT, let's say I want to predict what is the sentiment of a given review, and I have been given a movie review. What I would do is, for that specific task, I'll freeze whatever I have learned in my BERT encoder. I'll pass the sentence that I want to classify and add a small feed-forward layer here that would try to take the representation that comes out of BERT. So remember that we have this CLS token, which is like this beginning of sequence token kind of. So it is trying to encode all the information that comes from the entire sequence. So we take the CLS token and then we train the model only the added additional layer, which projects the CLS into the number of classes. So remember how with the encoder decoder module, we have the linear layer and a softmax at the end. We are doing something similar here. We are taking BERT's representation and then projecting it into the number of classes that we want to predict. So if I want to predict, let's say, the topic of the document, and I have 5 different topics, what I would add here is a linear layer that takes CLS representation and then predict those 5 classes out of it. So this is for, let's say, the segment or sentence prediction task. But what if I want to predict the relationship between 2 sentences? Let's say I want to do an entailment prediction, whether these 2 sentences are contradictory, they are neutral, they have a neutral relationship. What we can do is, since for the sentence prediction task, we had the class segment A, separator segment B, we just pass those as input. We again take the CLS representation, we add a linear layer that predicts those classes. And the main difference is we are only training on, we take the small amount of examples where we have ground truth. So let's say I have, for 2,000 examples, I know if the movie review is positive or negative. I'm only using that examples to train the additional linear classifier that I added on top of the representation. We are no longer fine-tuning the model anymore. Yes. So there is only encoder in BERT. We don't have decoder anymore. So remember that like when we were pre-training the model, we took, let's say, all English Wikipedia, okay? And we trained the model to predict the masks. And whatever came out of that, we freeze that model. So now this model has weight matrices learned that tells it if anything is masked in the input, what should be the correct token to be filled in. So my model has learned this representation about the input and it understands what the input is. Now, what I do is we introduce a new weight matrix. So let's say here, my CLS token, it's a D-dimension representation that comes out of the encoder. Now, I'm adding a linear layer that takes that input and then transforms it into two values, which is the positive and negative. And I take my ground truth, apply the cross entropy loss that we saw to update just that weight matrix. Now, I have this newer model that has BERT's pre-trained encoder and the linear classifier that knows how to, given a representation, a D-dimensional representation, what should be the class outcome of it. So when a new movie prediction, when a new input comes, I get this class, I now have the trained linear classifier, and it should be able to tell me which of the two classes it should predict. And we do this for every specific task. So I'll have a different linear classifier for my sentiment prediction task. I would have a different linear classifier for my entity, the entailment prediction. I would have a different one for document prediction. But what this is doing is only adding that linear layer on top rather than anything else. Does that make sense? Okay. And similarly so note that for each token we pass as the input, we have a representation after we pass it through the encoder. So we can even train a linear classifier per token and predict token level classes. So this can be important, for example, if we are trying to do named entity prediction. And for each token, we want to label whether it's what its class should be. So we can use the pre-trained model to do sentence prediction task, relation prediction between the two sentences. We can also do token level prediction task. For example, we can pass, let's say, a context and a question, and I'm trying to answer that question from the context. And for each token in the context, I'm trying to predict 1 or 0. And this is to let me find where in the context my answer lies. So I can frame this as a token prediction task. So using the same model, now I'm able to do different text understanding tasks. So given BERT's success in applying it to many different tasks, it didn't just inspire fine-tuning methods, it also inspired many different variants. So some wanted better performance out of BERT, other wanted more efficiency, and then there were other that wanted better training approaches. So just to give a few examples, with Roberta, it's a follow-up to BERT model. What they did was they did not change the architecture. They just trained the model on 10 times more data for much more longer duration. And instead of having a pre-computed mask over the data, they would recompute the mask at every epoch. So this was to let the model see the same text from different angles. And importantly, they also removed the next sentence prediction task. And this resulted in a model that was better in performance on downstream tasks than the BERT architecture, the BERT model. Then we have distal BERT. So while Roberta also released bigger versions of the BERT. So while there were people trying to make BERT bigger, better, there was also distal BERT, which was, can we compress the information into a much smaller model? And what they did was to take the BERT model, look at what its output is for every input, and then distill that information into a smaller model. So this smaller model was trained to predict the distribution that the bigger model induced on the input. And finally, Electra was a different variant where they were trying to make the learning more efficient. So the way they were doing that was, note that in BERT, what we are trying to do is let the model predict the 15% of the mass tokens. But we are not using other 85% of the tokens that are in the input. So what Electra did was to add a second module, a discriminator module, which would take as now the entire input with the mask filled, and then predict for each of the token whether it was original versus filled by BERT. So by adding this second discriminative module, they could now take a more holistic view at the resulting segment and get more learning signals out of it. So this was to improve efficiency in terms of what can be learned from the data distribution that we are enforcing. So far, like, we have treated BERT as mostly like encoder modules that come out of it, but what we can do is learn more about what's happening internally, which is what resulted in this subfield that we call BERTology, where the type of questions that we would ask is, what can we learn about training more efficient BERT? What information does BERT have, syntactic, semantic, or world knowledge in its learned at different layers? And can we learn anything about what its attention heads are capturing? So with BERTology, like, the main goal was to look deeper into what the model is actually learning after doing the pre-training step. So now we have autoregressive models like GPT that are great at generating text. And then we have models like BERT that are great at understanding text. But they're solving different problems. So can we do something better? So the thing that T5 introduced, which was a paper in 2019, was to unify. So we had, before T5, we had classification task and generation task. So we would want to predict classes, sentiment classes for a given text, and then we would want to translate, let's say, a text into other using decoder-only models. But what T5 proposed was to unify all tasks into text-to-text format. So if I want to translate, I would pass as input an instruction that tells what the task is. So translate English to German and the exact input that we want to translate, and then the output, which would be the translation. For if I want to summarize versus if I want to, let's say, predict, let's see. So if I want to predict whether a given sentence is linguistically acceptable, instead of predicting the two classes of acceptable, non-acceptable, I'll frame this as text-to-text task. And I'll say, this is my sentence. The output should be the entire sequence of tokens that map to not acceptable. So this was transformative in the sense that we no longer made distinction about tasks where we're predicting classes, whereas tasks where we were doing more involved generation. Everything was in text-to-text format. And this framework, it unified all the different things that we could do with a given model. So what they did to accomplish this was to train an encoder-decoder model, because note that everything is in an input text, output text format. So for its pre-training, so how do we actually train this encoder-decoder model? So what they did was to follow a similar recipe in spirit as BERT, which was, I'll take my input text, and I'll corrupt or mask out part of the input. And then the goal would be to predict as output the things that were masked. So this is similar in the sense that note that in BERT, we were masking certain tokens, and within the encoder, we were predicting what the specific token should be. But now, given that everything is a generative task, we want to predict, given an input sequence, what my output sequence should be. In the paper, they also consider many different variants of how this corruption can work. And you can find more details within the paper. But what they did was to take this C4 corpus, which is a massive amount of text data set, created this input-output format out of it, and trained the encoder-decoder module, as we saw in the previous slide. And what the result or the outcome of this model was, you could now use just this model to perform all and any task. You did not need any more to train this to add additional heads to either GPT or BERT. You could just prompt the model for the specific task you want to do and that you trained it with. So you take the T5 pre-trained module, and then you fine-tune it on all the tasks in this text-to-text format. And you could do all different things with just this one model, which was the real transformative thing that happened with T5. And at roughly the same time, while T5 was trying to unify all the different tasks that we can do with the pre-training data, researchers at Facebook, they were trying to unify the objectives that was, so there was the BERT's denoising objective and the GPT's generative objective. So the resulting model BERT, it corrupted the input, but let the model generate the entire input sequence. So the main difference with what we saw with T5 would be how the input-output is formatted. So we have the T5 model, which has now unified the different ways we do. Using a single model, we can do many different NLP tasks, including classification, generation. Now, with the GPT-3 era, instead of trying to change the model architecture, they took the idea of scale to a different level. So what they were doing with this was they took the GPT-1, they took the decoder-only model, as we saw in the GPT-1 architecture, and scaled it with 175 billion parameter models. And the most important discovery by making this scaled model training happen is we don't need task-specific training anymore. So remember that with T5, we have a pre-trained model, and then we are doing fine-tuning on the text-to-text format to make it do all the different tasks. But once we scale the model to 175 billion parameters, one thing that they found was you don't need any more the task-specific training. And in order to do the task, what you want to do is just provide it a few examples, which we now call in-context learning. So this in-context learning was manifested in many different ways. So one thing that you could do is zero shot. So zero shot is basically just saying, let's say I want to do translation. So what I would provide in this prompt is translate English to X. And then if I'm translating from English to French, translate English to French, and then the text that I want to translate. All I'm telling the model is what it needs to do, and I'm not doing any specific fine-tuning for this task. Alternatively, one thing that I can do is provided just one example. I can show what translation looks like. So I can show it, if I'm asking you to translate English to French, you have an English sentence as the input and a French sentence as the output. So when I give you a new English sentence, you have to generate a French sentence. So this is your one-shot learning. And the last one is where instead of this 0-1 format, you provide a few examples. So instead of giving it just one example, you can provide, let's say, 3 to 5 examples showing this is how generally this task is performed. And ideally, the model is able to use this information. So when we fine-tune the model, we show it thousands of examples. Here, with in-context learning, we are only showing 3 to 5 examples and letting the model activate what it has learned in its 175 billion parameters from looking at all the web text that is out there as to what task it needs to perform. So given these 3 different formats of in-context learning, one thing that came out of GPT-3 was what can scale do? So it's not that you are able to use the training to do in-context learning with a smaller model. You really need scale. So you really need to have that many parameters and trained with those many data set to enable the model to do zero-shot learning. So this was very good because now once we have pre-trained the model, we don't need anything else to be done. We can just provide it a few examples and let the model do the task for a new input that we are providing. And this led to what we now know as the prompt engineering field. And one thing we did in a survey just within 2 years was to organize all the papers that have come out in this survey, the prompt report. This was a work we did with my colleagues back at UMD, and we surveyed over 150 papers. There were already those many that were looking at how we can do better, more effective in context learning, just providing examples. So for example, if I'm doing translation task and I want to translate a medical term, and let's say I have a dictionary information somewhere that maps English terms to French for medicines. Just providing that additional information in the in-context examples, does that help improve translation quality? So there were many different ways you can provide the in-context example, you could form the prompt, you could form how to format the output, and these all were making a lot of difference in output quality. But if we are not fine-tuning the model, how does the model know what to do with those examples? So what's really happening under the hood? So in the paper by Min et al., what they tried to do was answer this question of what does in-context learning do? And the discovery was that the prompt, it's doing 2 different things. The first thing is recognizing what the task is. So when I say translate X to Y, this prompt, it acts as a query that tells us what it needs to do. And then the second step that happens is it activates specific things within the network that knows how to do translation. So what's happening with the prompt is you're activating part of the network that's responsible for doing that specific task that you want to do. But for a task like translation, given that it could be very difficult to do by just looking at a few examples, what's really happening when we are providing those few in context example? An alternative hypothesis that was explored in a different paper was, what is my pre-training data doing? So what if I went back to those billions of examples that my models learned during training? Is there any information that the model is recovering from? So it's not magically getting those translation capabilities. Sorry, question?
I wanted to ask, when you said task recognition, it activates the part of the network that's specific for that task. What do we mean by that part of the network? Like, is it a specific head, or like how? What is that specific part?
So you can imagine that what it's doing is, remember with the feed forward layers in the network, what we are telling the model to do is where to and what to focus attention on, and then we have those skip layers. I don't think that's what they investigated directly in the paper. That was the hypothesis that we were testing, but you can imagine looking deeper into the network as to what gets activated.
So like what words it looks at? Because I mean, we're looking at a specific task, and how does the model understand how to do this specific task just from a prompt?
Yeah, so that's what, like, at least with this hypothesis, the second hypothesis, what they are saying is if you go back and look at your pre-training data, you will find that you have many examples that are in the format that you are asking those questions on. So let's say if I have translation services on the web pages, they usually often have those format of English and then French when you're learning a new language, and you are crawling that information to train your model. So what this paper hypothesized instead was, we are just making the model go, like, activate part of the network that was learned during when it was optimizing for those specific pages.
So basically it attends to similar words that it saw during its training that was used for like to perform a specific
kind of, yes. Yeah.
Thank you.
So it's mostly like the model trying to navigate the messy pre-training data that it saw during the training process. It's mostly using that information to reactivate during the in-context learning. So how were the results like? So with the original GPT-3 paper, they showed that with this scale, you can do many, many different tasks. So for example, the Penn Tree Bank dataset, it was one of the dataset where reducing perplexity was the goal for the longest period. And by just scaling the model to 175 billion parameters and training it on billions of text, they were able to reduce perplexity on this data. Similarly, by using the few-shot examples, they achieved better accuracy on the lambda benchmark, where the goal is, given a long text, you want to predict what comes at the end. So this is what the lambda benchmark is testing. And by just training it on a huge amount of data, they got a very high accuracy on this task. And similarly, if we look at question answering, for trivia question answering, by using just a few examples in the prompt, they were able to achieve much higher accuracy than previous baselines. So once we had the GPT-3 model, which was capable of doing all these different tasks, what we have seen is, given that we don't know how these models are trained and what's the actual learning that's happening underneath, we have now a surge of pre-trained models across different labs, industries, where everyone has their version of a decoder, a GPT-3-like model that is capable of doing many different tasks. But one thing that I want to mention that is important is, as this progress has created many different models that we can now use for many different tasks, including the language coverage that they provide. So for example, you can have a language-specific GPT that is trained only on, let's say, Hindi text, so it understands Hindi. But how do we actually measure and understand what these models can do? So note that the old models are no longer sufficient because we don't know what these models are capable of doing. So unlike before GPT, we knew what tasks we cared about. So we could do sentiment analysis, translation task, and we were having models optimized for these very specific things. But now, given that scale gives us the benefit that it gives, we no longer know what these models are truly capable of doing. So our evaluation benchmarks might not be sufficient. The second thing is, because that the data set that we use for these benchmarks they have been online. We don't know whether the model has already seen that during training. So whether its capabilities come from just knowing what the input-output should be. A model can be accurate, but also toxic at the same time. So you can ask it questions that might lead to responses that are unethical. And finally, given that they're doing this generative task, if I'm asking it to write a poem, how do I even evaluate whether the poem is correct or not? So evaluating these models, they have emerged as a very important research field. So just as a side note here that as we are looking through all of these models, we should also be thinking about how we are evaluating these models. So far, we have only talked about how we use pre-trained language models for processing text, but we also, like I mentioned at the beginning, that we can actually use transformers to do many other things. So one of the things that we can use it is to process images. But remember that your image is a 228 by 228 pixel, and you cannot have every attention over each specific pixel. So what this paper did, in order to use transformers in vision, was to take the image and then divide them into patches. So instead of looking at an image as a grid of pixels of 228 by 228, we look at all the patches that make those images. So once we have those patches, we pass them through a linear layer to project them into flattened vectors, and then we add position as to where those patch occurs. So once we are able to process an image as a series of tokens, like we were doing with text, we can apply the same module as we did with, let's say we can use a transformer encoder and train it to predict the class. So this is how we use transformers for images. Question?
I have a question about the in-context learning. You said that for models like GPT, we can scale up the models and just use some prompts for specify our task, but for specifying our task. But I think in most of the LLMs that we have a SFT part that we try to do some supervised learning for them. So why don't we try to make some template and then ask the users to just use these templates if they want, for example, do name entity recognition, just use this context or this prompt for this specific task. Because using SFT, we may add some bias in our models because it tries to behave in our supervised task, I think.
So is the question that generally, so we talked about how we don't need to do any task-specific fine-tuning, but we do, in practice, we do have the second step where we are fine-tuning the model on some instruction and what the output should be. And I would say that at least depending upon how you fine-tune the model, the thing that happens is when you have a pre-trained model and you provide in-context examples, the accuracy of the model based on the input that you provide, because what it is trying to do is find information that it has learned during pre-training to get to the answer. Any small changes in the prompts can lead to a bigger changes in the response. So with the supervised fine-tuning step, what we do is make the model more focused on a set of tasks that we care about, that we want the accuracy to be consistent and of generate high quality output. So let's say I want to now use the model for translation, and I want to make sure that it does the translation task correctly. I can do a supervised fine tuning on the model to make it make it overfit to the translation task. So what happens with this stage is it might forget the information that it has learned before, but how you set the supervised fine tuning step also matters. If you train it with one specific prompt, you have to provide that prompt to the user to make sure that the model is used correctly afterwards. But you can also train the supervised fine-tuning step where each input can be mapped to, let's say you collected 20 different instructions. And each input is mapped randomly to one of the instructions, then it doesn't overfit to the very specific pattern that you're providing in the prompt. So there are ways to mitigate that.
So for models like ChatGPT, that is general purpose model, it's not too good to use just some SFT because it can remove the generalization, you know?
No, but like you do, so you start with the pre-trained model, you do the supervised fine tuning to activate the set of tasks that you care about, and then you also do a reinforcement learning step to reinforce good and bad behavior. So the thing is, because it learns all this data set from the web, it can learn toxic behavior, it can learn to do random things from the messy web data that you used it to fine tune on. So the final step, it's telling it what good and bad behavior is. The exact recipe of ChatGPT, it's unknown. So we don't know how many steps and what steps happen at each step, how the reinforcement learning behavior is enforced, what tasks they are covering. But the general idea is that with just the pre-trained model, while it has those behaviors where you can provide some examples to activate the behavior, the inconsistency of the model behaving differently for different inputs and with small variations in prompt, they make it very difficult to track performance in practice. So we need those additional steps to make sure that the model behaves correctly, if that makes sense.
So first, a fine-tuning process, then maybe SFT, and in the last, RLHF, yeah?
That's a potential recipe. I don't know if that's the recipe.
Yeah, thank you.
So now we have seen how we can use transformers to manipulate, to apply the same thing that we did with the text by considering an image as a set of tokens, where each token is a patch, right? What if we want to do the same with audio? So what we do with audio instead is once we have the waveform, we first normalize it, and then we pass it through a small convolutional neural network, which encodes this waveform into features. And note that this is just one specific way of doing it. Now, this feature vector, what comes out of this network is a set of feature vectors that each represents a small audio sequence. So let's say my audio is 1 second long. My embedding vector would have, let's say, 10 different vectors, each corresponding to a small patch of the audio. And then once we have those patches and feature vectors, we can pass it through the same transformer architecture as we saw before, because at the end of the day, what we want is feature representation of how our input looks like with the information on where the input is coming from. So an embedding representation of the input plus a representation of the position where it belongs. So, so far, we have looked at how we can process image, audio, and text with the transformer model. And what the question here is, can a model learn not just to perceive, but also to act? Can we make the model take decisions like we did with reinforcement learning? So with reinforcement learning, you have a state, and you want to take the action that maximizes a reward. But how do we use transformers to do that? So the way decision transformers work And this is the application of transformer in reinforcement learning is you can convert given that now you can represent anything as some feature representation that you can pass through your input. You have a sequence of reward, state, and action. So at every time step, what you're doing is, let's say I have a game and I want to predict what action should I take next in order to win. So imagine the snake game, for example, and you're trying to find the action that would make you find where the fruit is in the box. So you can represent the state as the image patch that describes where the snake is currently in the game. And now the action that you can take is go up, down, left, and right. But at the end of the day, so let's say you did many simulation, you played it, and you collected a sequence of if I go up, I get a specific reward at the end of the game. What we can do is organize this sequence as reward, state, and action. So during inference, what we can do is tell the model that I want this specific reward from my game. This is my current state. Give me what the action should. And using the simulations that we collected, we can form our training examples in the same way. We can play the game. We can figure out what, given the state, given the action, what my reward should be. So by just transforming this entire navigation into a sequence of reward, state, and action pairs, we can actually use transformers in reinforcement learning as well. So now, as we have come full circle, we started with transformer as a tool of language, but we have seen that anything that we can tokenize, we can pass as input to the transformer models, and we can learn how to generate output out of it. So we know that transformers can read a text. Using the decoder-only models like GPT, we can train the model for it to predict the next token in the sequence. We have seen how we can use images, patch them into tokens, and pass the position to predict what the class of the image should be. We have also seen how we can pass audio spectrograms, extract feature embeddings for part of the audio sequences, add position embeddings, and then let the model generate what the audio was saying. So given that we can process all of this information, what we can do is use this model to process multimodal information. So we have an audio encoder that processes audio information. We have a vision encoder that transforms image patches into a sequence of embeddings that my encoder can take to generate a text. I have a text-only model that takes as input text tokens to predict what the final output should be. So this is just like one other representation of passing everything to the transformers, but using mixture of experts, because this is what we also use in the current foundational models where part of the network that is useful for activating a specific information gets activated during inference. So as we have seen, the current foundational models, they are being used in many different applications spanning healthcare, law, marketing, education. I'm pretty sure people use it. I use it for correcting my English, for getting information about specific topics. So using just the transformer architecture, as we have seen, the main thing that changed was we could scale this model. We could train them more efficiently. We could do inference efficiently by using caching mechanism. We could take the transformer model to process text, images, and audios. And all these capabilities combined together is what gives us the current models that we use every day in practice. So with that, I would end the second part of the talk. Happy to take questions on this. Um,
Thank you for your talk. I had a question before, but I hesitated because I didn't know how long it would take. I mean, if we had time to explain that. I was wondering what happens in distill BERT or like similar models that would allow us to keep performance high while making the model small and more efficient. Like how are they trained?
Yeah, so one hypothesis whenever we use distillation is that in real world, we can have an information represented in many different ways. And as we train a model from scratch, we don't retain all the information, right? We retain what is a compressed representation of the initial input. Now, the initial input can have many different forms. So I could have, let's say, 5 different ways of saying a very specific sentence from English to French. But what this final model that is trained from scratch, that does not distill any information, is have maybe a few ways to do that. It doesn't retain all the information. So what your bigger model, the first model that you train gives you, is a simplified version of all the things that you trained it on. And what happens when you distill the model is you're not trying to retain all the information from all the text. Given that this model has learned what a correct behavior should be, you are making the task simpler for the smaller model. So you're only showing it a specific part of the things that the bigger model has already learned as a part of processing that huge amount of information you begin with. So that's how in practice distillation can work, in the sense that even though you're distilling information from the big model already has distilled some information from all the things that it has seen from the web.
Thank you. So a follow-up question would be, how does the model decide what to keep and what to discard? Or is it the humans who filter the data or?
So no, as you're training the model, you're making it learn what the next token should be, right? So you're showing it millions of examples to say, given this input at this time step, this is what my token should be. And when you compute the loss, you're nudging the model so that it knows what the correct output should be at this time step for this input. But you're making small nudges over the training over a million of examples. So this is not, it's as a part of learning from this very diverse data that you're only retaining part of the information because you're moving those weight matrices around as you backpropagate through the network. Is it? Yeah.
Thank you.
Hello, thank you. I have a question. So in speech self-supervised learning models like Hubert or WaveLM, you can observe through linear probing that different transformer layers are more task level aware. For example, some capture speaker identity better, some capture better, like the phones understands the phone, or like the language specific, like sentences. Is this also present in like text-based language models, and that would it help in big language models to maybe look for transformer layer specific for what you are looking for, even for diminishing the dimension of the network?
Yeah, so this is what I briefly mentioned in the passing, but that's what we study in BERTology, for example. So what we do there is to look at specific heads of, let's say, BERT, and see whether it captures syntactic information. So if I were to take a specific layer and take the representation from that specific layer and predict part of speech stats using layer 1 versus the final layer. If I get better accuracy at a specific layer, we kind of say by probing that specific hidden representation that this head might be responsible for capturing more of the syntactic information. So we do have, at least in text, a lot of exploration in that direction as well, where people have looked at what specific heads of BERT captures, which heads are responsible for capturing numerical knowledge, which heads are responsible for capturing part of speech information, what captures semantics. So it's there. It's like, but for example, you can do that with the smaller models. I haven't seen, or I don't know of such analysis as like the GPT-3 scale. Like if you have a 175 billion parameters model, it's very hard to say where and how the information is localized.
Just a small follow-up questions. How does this link to mixture of experts? Like, do the mixture of experts actually solve this problem by not having to search for the good head that does that, but the mixture of experts actually solves this problem?
So I would say it depends upon how like you can have experts defined in many different ways at the end of the day, right? Like, so imagine even if I'm trying to process English text, let's say I have domain specific mixture of heads, and I know where I want to route on, but at the end of the day, like there might be information that's, I think it's doing what you said, which is activating smaller part of the network that's highly specialized for that information. I don't know if it completely solves the problem, but it's a step in that direction as to by having the same number of parameters, but like focusing those specific parameters on different subtasks, can you actually know what's happening? But I don't have a lot of depth in that specific topic.
It's very good. Thank you so much.
I have a question about the multimodality in transformer. Is it possible to have a end-to-end multimodal transformer for different modalities without any paired data?
So it depends, I think. So imagine, let's say, it depends upon the kind of input, right? So because, for example, if you're thinking about PDFs, they have both text information as well as images in them. And if you're thinking about, let's say, subtitles, you have images and text as well as audio in them. So depending upon what your source is able to capture and how you're formulating what your input and output should be, you still need those encoding for different encoding for the different modality, right? At the end of the day, you still need to process your audio tokens differently from the text tokens. I think the multimodal models that I have played with, like they use different modalities as input, but they are still trained to generate text at the end of the day. And there you can have mixed information from multiple modalities in the input, but I don't know if it would be as straightforward to, like generate text, add image, add audio. It's not very clear to me.
Because I think now the Sweta models that now we have try to translate every information into text, then again into different modalities that we want. For example, if we have audio, we want to analyze it, we should have some text about it, Without it, I think the good models that we have nowadays, they can't work with just audio without any explanation about it or without any transcript. But 2 months ago, I read a paper. It was about 25 June 2025, I think last month. They published this paper last month named Harnessing the Universal Geometry of Embeddings. But they are talking about the security of embeddings, because they said that if we have a vector database without any extra information about it, without any documents, or just we have an unknown vector database, we can extract the information that are inside this vector database by just using some diffusion models to and we can set the known models in specific modalities like text, and by using this diffusion, we can transfer information from this unknown embedding to that known model that we have, and then ask it to generate to understand what happened in unknown embedding, by diffusion.
Yeah, but like I would say that so far, what I have shown here is how you can encode different modalities together, not on the generation is still text-based. I think what they're doing in that specific paper, it would be hard for me to say anything about it without having the background. So like specifically what they are doing with diffusion models, like I don't have enough information on that.
But in text modality, for simplify it, we have different languages. We can suppose that they are from different modalities because the characters are different. If we don't have any pair data, we can suppose that these are the two type of different modalities,
Yeah.
But we proved that by training LLM using both type of language, we can have a good translation for both of them. So maybe for different modalities also we can do this. And maybe but I think the main problem is tokenization or mixing the input.
Yeah. I mean, even if you were considering multiple languages as different, they are still text. So there is still like the representation, they would still be closer for them rather than the same text. I don't know if this is true, but like if I have a text and an audio saying the same thing, to what extent those representations are exactly aligned, it's an open question.
Can I ask a private question about Google?
Go for it. I can choose not to answer.
Is there any part there that try to work on end-to-end models for different modalities?
Sorry, could you repeat that?
Is there any group there that try to work on this specific topic for having a large model for all of the modalities, not just text?
I would say yes. Yeah.
Is there any person there that I can speak?
I think I would need to check that, but there are definitely people doing multimodal stuff at Google.
Yeah, thank you.
So thank you. Thank you for the presentation. So I guess my question is transformers always the solution? For example, for speech, I've read about how Shazam like recognizes music, and I think the algorithm is really cool. It like uses Fourier transforms, it decomposes every frequency, and then it matches to the vector to the databases of the music. And I think it's really cool algorithm. And I don't know if transformers will basically solve this task as well. So basically, my question is transformer always the answer to everything? So yeah, that's.
Yeah, so I didn't show this, but I had this previously in my slides, which was let me try to bring that if it still exists. No. So there is this poll. I don't know if you have seen, which is attention or is transformers all you need? And there is this web page that's tracking whether we would have a different, better architecture that could also fundamentally do different things together. I think the good thing about transformer is that's lacking with the other architecture is just being able to have information from different modalities or tasks grouped together. And that's a strength that it's not clear whether alternative architectures propose it, but it's not the case that we do still have, for example, hybrid models that have transformers as well as recurrence in order to do some of the tasks. So depending upon what you're aiming for, it's a component that you can add with some other things that you want. So it might not be the only solution, but it's important in that it is able to seamlessly handle different things in the same module. I think that's the core component that is missing from alternative architectures.
With regard to the previous question, what can you tell us about the ability of these models to do mathematical operation, and if you think that these models will be as reliable as actual calculators?
Sorry, could you repeat that?
With regard to the previous question, we were talking about all the things that can be done by this model. I just want to ask, what do you think about the abilities of these models to do mathematical operations? And if you think that maybe in the future they will be as reliable as actual calculators to do, I mean, everything in mathematics, like integrals, limits, derivatives, and so forth. Thank you.
Yeah, so I think we do know that they have those capabilities to some extent. Like you can do mathematical reasoning things. For example, I don't know if you followed Twitter, we had this news a couple of days ago where on Maths Olympiad, many LLMs did very well, competitive, like I think there were 1 or 2 models that solved 4 or 5 problems out of the 6 problems that were given. So there is like capabilities that they can process information and provide proofs. The thing is, we don't know. We can make that work by showing it, let's say, similar proofs in the past. We know what we can provide to improve, but we still don't know how brittle this capability is. Like whether to what extent I can take this model and apply it to any mathematical task, it's unclear. So one thing, like for example, there was not even mathematical questions. Like if you were asking to count R's for a word like strawberry, the thing is the way these models tokenize things also make a difference on what they can give you as the output. So there are like things that you can do to trick the model into doing the correct thing where, for example, for strawberry, you would say, spell it out character by character so that tokenization is no longer a problem, and then tell me the number of R's. So that's one way. This is all to say that we still need human in the loop for these language models to activate what we consider are capabilities of these models. I don't think it's reliable in the sense that you need human effort into making sure that the correct pattern is induced. So there is still like some way to go there. There's still a lot that we can do to improve.
Do you think that it will be feasible to create maybe classificator that can understand the mathematical problem and then rely on an external calculator, just like a tool augmented agent?
So I think like we partly do that, right? Like at the end of the day, there are models that nowadays do thinking, and they are like trying to understand what the problem is. And you also have those tools integration. You can search on the internet to answer a specific question. You can refer to an API. Like for example, imagine doing this. Let's say you want to use a specific Hugging Face model. You want to use a specific model to do a specific task. And these models are capable of processing the request, calling the API for you, and then returning the answer. Depending upon what your tool is doing, I think you can, I don't know to what extent you can just completely get rid of the tools to do all these steps in one go, but we are already definitely doing part of this mixed processing. Like if we know certain things can give us deterministic good answers, for example, calculator in this setting, and I can process, all I need to do is use the LLM to process what needs to be passed to the calculator just so that I make sure that the calculations are correct. We already do that. But ideally, I think it would be nicer if you needed minimal tools from external, because depending upon the task, you might want to use 5 different tools, 10 different tools. To what extent it's manageable? The whole human in the loop pipeline of getting a task done also shows us that there are things that can be improved with these models. Yeah. Go ahead.
Hi, hello. Thanks a lot. I have like a sort of like specific question. I would like so you know like a lot of like the newer models, like they alternate like local attention, global attention, blah blah blah. So there's like this you know, and I double checked just now to make sure that I was like recalling this correctly, because like so Gemma 3, what they do is like they have 4 layers of local attention, and then they say we have a layer of global attention, and then 4 more layers of local attention, global attention, and they do that. And they say, well, this is like much more efficient, like memory wise. But I mean, so what I think is like there's something I didn't get here, because like so if you have global attention at any point in your like layers, then you're like, just imagine that you have like 1 million tokens, you're gonna overflow anyway, like your memory, right? Like so that's what I don't think I got really. So how do they like make the model more efficient if they still do global attention? Or I imagine they optimize that somehow, but how?
I don't think I have the complete information on that, but I would say, and maybe I might be incorrect on this. So I think it's the replacement of global to local attention that adds efficiency rather than local to global attention. So by default, you would do global attention. And what you're doing instead is for specific layers, you're now doing local attention. So let's say I'm only allowed to see 3 more tokens in my current neighborhood for the first few layers. But when I go to my 4th layer, I'll allow the model to compress all the information it has learned by looking at all the other things that came later on. So generally, you would do global attention. So my input should be able to see everything else that follows, right? Even if I'm talking about what it encodes as information. So it's the replacement in the other direction. And if you think about the replacement in the other direction, that's adding efficiency, right? Because you are not looking at everything. So you're not doing all n-square computation. You're only, for specific layers, you are reducing that to k-square computation. And then only after a certain number of layers, you're doing the actual n-square computation.
But I mean, so like still, so like the problem is still there, I think, because like, so maybe I didn't get you, but like so like if you think about this, like just imagine you have local attention and you just look at 10 tokens, so that's manageable. First 4 layers are okay. Yes. But then you get to the 5th layer, and that's where you do your global attention, and you know, suddenly you run out of memory, because like you don't have memory to do like the global attention. So that's what I was thinking. Maybe this is like too technical, I don't know. But I was just thinking this doesn't make sense. Like
there is efficiency in terms of number of computations done, and then there is efficiency in terms of the memory used, right? So you have the number of computations that you did in order to reach a final answer. It's related to, but slightly different than how much memory you have access to. Imagine you have enough memory to support all the global attention. And let's say then your total compute would be of the order of n-square computation if you do global attention at all layers. What you're doing here is just reducing the number of computation without regarding. So the memory here would be slightly detached in that. It's assuming you could do all the global attentions. You're only reducing the number of global attentions that you do at specific layers. Does that make sense? So
Th-
it's
I mean, yes, but you know, like you're still gonna run out of memory when you get to the huge computation. So I
not,
don't know. Maybe
yeah.
sorry. You know,
It's
like
okay.
I'll just cut it here because it's maybe too technical, and I should just try to do more reading on my own. But I was just curious to know, like, if you had like any information. But I'll cut it here. It's 12:30, so I think we all want
Yeah.
to go have lunch. So sorry for.
No, it's okay. It's okay. Yeah. Right. Thank you.